Okay. Now we're going to assume that we have an orthogonal set of eigenvectors. And if we do, then we can write down our column of eigenvectors matrix here. That's our P matrix. And then we can write down our diagonal matrix with the eigenvalues. So we can pick our eigenvalues, and then we can write down the inverse of the P matrix, which, since this is an orthogonal matrix, meaning the vectors are all normal of magnitude 1 and orthogonal, each set being each column representing a vector whose dot product with any other column is 0, so they're orthogonal. These are orthogonal. That means that the inverse of the matrix is equal to the transpose. Now that's another proof. I'm going to accept that for right now, and hopefully you understand that proof as well. Okay, so P inverse equals P transpose. So now what we're doing is we're doing the usual change of basis. In the eigenvector basis, this is our transformation matrix. If we want to do this relative to the standard basis, then we're going to have to start here with our standard basis, come up to our eigenvector basis using the inverse of our column of eigenvectors matrix, and then apply the diagonal to take us across to do the transformation in the eigenvector basis, and then bring it back down to the standard basis with our orthogonal matrix P. Okay, our column of eigenvectors matrix. Again, you should understand exactly why this transformation does what it does, so you understand why this transformation does what it does. Right now we just accept that. Okay, now I've written these vectors, and let's be sure we see that this is a transpose of this. Okay, this is just written with vector v1 being v11, v21, down through vn1. Second vector v12, v22, down through vn2. Last vector v1n, v2n, down through vnn. So that our rows are v11, v12 through v1n, v21 through v2n, and so forth. The usual order of subscripts in a matrix. Now, if I want to change my columns to rows, then my first row should go from v11 to v21 to vn1. Well, it does. v11, v21, vn1. Okay, my second column should be equal to my second row, or my second row here should be equal to my second column here. You can see that it's so. And last column, last row. So these matrices are transposes of one another. And again, this relies on this being an orthogonal matrix, so that we know that its inverse is equal to its transpose, so that everything has the meaning that we intended to have. Okay, I'll be more explicit about that, but I'm not going to. Now, I'm going to multiply this matrix by this matrix. Okay, so lambda 1, and this is lambda 1 followed by a bunch of zeros. We multiply that by the first column, we get lambda 1 times v11 plus a bunch of zeros. So we get lambda 1 v11, that's all we get. First row times the second column is lambda 1 times v21, so there it is. First row times the last column is lambda 1 times vn1, everything else gives us 0 because of all the zeros here. We get lambda 1 vn1. Now, second row times the first column. Well, we got a 0 here. I haven't written all the zeros, but we understand what we're looking at. The second number in this row is lambda 2. It'll multiply the second number in this column, which is v12. So we get lambda 2 v12. Then the same row times the second column, we're going to have lambda 2 times v22, and so forth. So we're going to end up with these numbers across the first row with lambda 1 in front of every one of them. Okay, in the second row, we're going to have these numbers, but with lambda 2 in front of them. In the third row, we'll have all the numbers in the third row here, but with lambda 3 in front. When we get down to the last row, we'll have lambda 1 in front of every member of this row. So that's the way the first multiplication works. Now the second multiplication gets a little longer, and you know, I hope you can follow what I've done here. So this first sum here is going to correspond to this first row by the first column. So let's look at how that arises. First row times first column. First number in the first row of this matrix is V11. First number here is lambda 1 V11. Multiply them together, we get lambda 1 V11 squared. Okay. Second number in this row matches up with the second number in this column. We have a V12 and a V12. That gives us a V12 squared, and of course we've got our lambda 2, so we get lambda 2 V12 squared. The third number here is going to be V13. The third number in this column is going to have a V13, and so forth. So what we're going to get is we're just going to get V11 squared and V12 squared and V13 squared on up to V1n squared, but with each of these multiplied by a different lambda. Okay, with V11 squared multiplied by lambda 1, V12 squared by lambda 2, and so forth. Well, that's going to happen, and it's going to happen similarly on every diagonal. If we multiply the second row by the second column, which I haven't done here, well, you should do that and condition yourself with the way it'll come out. We'll still have lambda 1 and lambda 2 up through lambda n because we have all those in the second column. And our V21 is going to match up with V21, V22 with V22, so we're just going to get a bunch of squares, and so forth. Okay, now if we're not on a diagonal, things don't match up in quite the same way. We don't get squares of our V11 through V1n or V21 through V2n. So let's do the second row times the first column to get this number. V21 is going to multiply V11 and lambda 1. So we get V21, V11, and lambda 1. And then V22 is going to multiply lambda 1, 2, V12. So we're going to get a V22 and a V12. There's a V22 and a V12. And we're going to get a lambda 2. And then next one, we'd have V23. And that would match up with lambda 3, V13. So we have V23, V13 times lambda 3. And that's going to continue up to the point where we get V2n times lambda n times V1n. But this establishes the pattern in a way that will make things believable. Now, I want to check and see if this matrix is symmetric. Okay, so what's on the diagonal doesn't affect the symmetry, but what's above and below does. This is below the diagonal. It should correspond to the next number above the diagonal in the first row. Okay, so the number we get after we get this one, what we get, in other words, when we multiply the first row by the second column, should match, if the matrix is going to be symmetric, should match what we get if we multiply the second row by the first column. Does it? Well, we get V11 and a V21 that match up with a lambda 1. So we get lambda 1, V11, V21. That's easy enough. V12 and V22 are going to match up, so we're going to get a V12 and a V22. We're going to get a lambda 2 here. Okay, then we're going to have a V13 multiplied by what? V23. So we're going to have a V13, V23, and that's going to be the next one down here. It's going to have a lambda 3. So that's the pattern that we're going to get. Now, let's see where we are. Well, we got lambda 1, V21 here. We got lambda 1, lambda 1, V21, V11. We've got lambda 1, V11, V21. Well, there's a V11 both places. There's a V22 both places. There's a lambda 1 both places. So this matches this. Now, is that a unique thing that happened just on the first element? Could have been. Let's check the second element. Okay, here we got a lambda 2 and a V22 and a V12. We want to compare that with the second element here. Okay, lambda 2, yep. V22, yep. V12, yep. Now they're in a different order here, but order doesn't matter in multiplication. And then we can verify that this one matches this one, and now we're getting pretty convinced, if we think about what's going on, that everything's going to match up, and this is going to be the same as this, which is strong evidence for symmetry. Then if you understand how the subscripts are matching up and why they're matching up, and it comes out simply because this column is the same as this row. Every column here is a row of this. We're essentially multiplying all the rows of this by all the columns of this and putting them, each product of row and column ends up going in two places in symmetric positions on the matrix. Now I leave it to you to experiment with this and fill in this proof and hopefully put it into acceptable mathematical notation. All I'm doing is pointing out a pattern here. I haven't really put it in what would be generally acceptable mathematical notations. For example, this could be written as the sum of lambda I v careful. Okay. If 3 is our I, this is the I, and this is the I. So it's going to be V, J, I, V, K, I. Sorry, VJI, VIJ. And for J equals 1 to N. Sorry, for I equals 1 to N. Okay. So we're going to get, and don't take that literally, think about whether that's actually true or not. We want to be very careful the way we do this. And we kind of want to start with, well, I'm not going to say any more about it. So we have to kind of write each of the elements in terms of some sort of a summation, and then show that they're identical. Okay. Anyhow, that's an indication of how we prove that when we do this with orthogonal matrices, diagonal matrix transposes the orthogonal matrix, we get a symmetric matrix down here.